Hello and welcome to this video about determinant proofs. In this video we'll prove this equation. The exponential function isn't like raising a matrix to the power of a number. This is because the exponential function is a power series that has additions in it. That stops this from happening. We'll prove a lot of things in this video, most of which will lead up to proving this equation. So the first theorem that we'll prove is that raising matrix A to the power of an integer like this will be able to be written like this. The change of basis matrices P and P inverse can be written without being raised to this power like this. Now to prove it, we'll raise A to the power of K and substitute this expression in for it. Raising this expression to the power of an integer K gives us this expression multiplied by itself K times like this. We can then remove all of the brackets. All of the P inverse pairs cancel out, leaving all of the J's next to each other like this. There are K J's next to each other. We can write K J's next to each other as J raised to the power of K. So that's it, we've proven this equation. And here's a second version of this proof. This time we're using induction to prove it. Firstly, we'll prove it true for K is equal to 2. We'll firstly square A and substitute in this expression for A. Squaring will give us this expression, and there's no need for under brackets or dots. And this inverse pair of matrices cancels to give us this. Simplifying this expression gives us this expression, which proves it true for K is equal to 2. Now we have to prove it true for K, assuming that it's true for K minus 1. We'll raise A to the power of K and then substitute in this expression like before. We can split this up into two bracketed expressions like this. We can make this substitution for the expression in the second pair of brackets, because we're assuming this theorem true for K minus 1. Then we can remove the other pair of brackets. This inverse pair of matrices can cancel to give us this expression. Finally, we can multiply these different powers of J together to give us this expression. So we've proven part A of this theorem. Now to prove part B of this theorem, that if A is raised to the power of minus 1, then this equation is true. We don't need to use this to prove the exponential theorem, but it would be good to prove it anyway. We have to show that this expression is both a left and right inverse of A. This is the way to prove most inverse proofs. So now to show that it's a left-hand inverse, we'll multiply it by A on the left and substitute the expression we had in for A. We can get rid of the pair of brackets. This pair of matrices form an inverse pair, so we can eliminate it. After we remove this inverse pair, we get another inverse pair that we can eliminate too. And then we get a final inverse pair that we can eliminate so as to get the identity matrix. So we've shown that it's a left inverse of A. We had 3 inverse pairs that we had to eliminate in 3 steps. Now to show that it's a right-hand inverse. This time we'll multiply it by A on the right. Then we can substitute this expression in for A. We can get rid of the brackets. We can eliminate this inverse pair, which will leave us with this inverse pair that we can also eliminate. And so we'll get this final inverse pair that we can eliminate so as to get the identity matrix, thereby completing part B of this proof. Now to prove this theorem for negative powers of A that are of magnitude 2 or greater. So now to start this proof, we can get this expression which we can do with exponents. We'll substitute this expression in for A. We can do this exponent trick with J this time. The inverse of an inverse gives us the same matrix back again. We've proven this in a matrix proof video. And we can put these indices back together to get this expression, thereby completing part C of this proof. Now to prove this statement for power series, that we can get this equation for A if the function f can be described well using a power series. So now to start this proof, we'll substitute this expression in for A, which will give us this power series. We can invoke part A of this theorem to manipulate this expression to be this. Notice that J raised to the power of 1 doesn't need to change. We can put these change of basis matrices on either side of the identity. Now we can factorize this power series so that the change of basis matrices are outside the brackets. We can then express this power series as function f, thereby completing part D of this proof. Now to prove this result for any power series, that the determinants are equal for the function f applied to similar matrices. So now to prove this, we can get this statement from the previous part of this proof that we've just proven about half a minute ago. We can apply the determinant to both sides so that this statement is true. We can get this product of determinants using a pass theorem. We can move this indice outside the determinant function like this, according to a pass theorem. Then we can swap these two determinants around because they are either real or complex numbers. And these two scalars cancel to give us this determinant, which completes part E of this proof. So now to prove part F of this theorem, which is a bit more complicated and needs diagrams. It says that the determinant of a function applied to a matrix in Jordan canonical form is equal to the product of this function applied to the eigenvalues of this matrix, which are the diagonal entries. So there are two cases. In the first case, this Jordan canonical matrix is a diagonal matrix, which is a special case of these matrices, and so we'll call it D from now on. And D can be written like this, its entries being its eigenvalues. And we can draw D like this as a matrix with a generalized size. If we apply a function f to this matrix, we'll get the diagonal of the function applied to its diagonal entries. I'll just make some more room on the screen like this. And this is the function f applied to D, drawn as a matrix, as it would look as a matrix, and with dots because we'd be unsure of its size. So this is its determinant. It's the product of its diagonal entries, which are this function applied to each of the entries of matrix D. And we can write it using this product notation like this. And now we'll look at the case where J is a Jordan canonical matrix without being a diagonal matrix. So J is called a Jordan canonical matrix, so usually when we say this, it means the case where it isn't a diagonal matrix, even though it can include them. But J has a structure. It has some ones along its superdiagonal, that is, the diagonal just above the main diagonal. But the entries adjacent to this one in the superdiagonal must be equal. So being a Jordan matrix is constraining, but they are more difficult to work with. We can write it out like this using the Jord function, but this doesn't tell us where the superdiagonal ones are. We can write it out as a matrix, and we can see where the superdiagonal one is. It's written in red and circled. Notice that lambda 1 must equal lambda 2 if J is to be a Jordan canonical matrix. And applying a function f to it causes the diagonal entries to be f applied to these entries. All of the entries above the diagonal are affected and can be non-zero. I've used the function UTM, which stands for upper triangular matrix. It would need more information like the values of all of the entries in this part of the matrix. So this is how we'd write out f applied to J. It's an upper triangular matrix, and the upper portion of this matrix can have non-zero entries. I've used stars to stand for entries that can be non-zero. And the determinant of an upper triangular matrix is just the product of its diagonal entries, which in this case is this. And then we can write it out using the product symbol like this. So now we've proven part f of this theorem, because there's only two cases. So now to prove this theorem, that the determinant of a function applied to a matrix is equal to the product of the function applied to the eigenvalues of this matrix. An eigenvalue can occur more than once, and in this case we'll include it in this equation more than once. Now to prove it, we can get this result straight away from this earlier part of this theorem. And we can join it with this other result from another earlier part of this theorem. So that's it, we've proven it in only 2 steps. We can also express it in product notation using the product symbol. So now to prove the main result of this theorem. The determinant is replaced by the trace function after it's been swapped. We'll apply this result that we've proven just a short while ago in this same video. We can use it because the exponential function can be comfortably approximated using a power series. This is a property of exponentials, that the product of exponentials can be merged into this one exponential of the sum of all these eigenvalues. And the sum of these eigenvalues is just the trace of this matrix, which is equal to the trace of A. There's no need to reference the matrix J in this proof. We can also prove this, but we can't simplify it into anything nicer. We can prove it using a past result in just one step. In fact, we can do this for any function that can be approximated well using a power series. And I'd just like to write down this result using the product symbol. I'd just like to prove this result for the logarithm function, which doesn't get approximated well with a power series. It does break down for certain numbers, so I'll do it separately. So we'll start this proof from the left-hand side and substitute in this value for A in terms of the Jordan canonical matrix J that it's similar to. This is a property of logarithms that we can use. We can move the minus sign outside of the log function like this to multiply the function by -1. And these two logarithms obviously cancel. And we can use a past part of this theorem to give us this result, which is what we want. So we've proven this part of the theorem. And I'd just like to write it out in product notation as well. And we've finished the whole proof. So I'll just draw in the little black box that says that we've finished the proof. So I hope that you found this video to be helpful and insightful. Please click like and subscribe if you did. Feel free to write anything helpful in the comments and to share this video. And thanks a lot for watching.